हेलो एवरीवन। आज के इस वीडियो लेक्चर में हम लोग सॉल्यूशन का पार्ट 2 कवर करने वाले हैं। इन दिस वीडियो वी आर गोइंग टू कवर अप दोज टॉपिक्स which are depending upon the solutions behavior in real conditions, okay, and also we are going to see the properties that are deviated from ideal behavior, and here we will understand two new topics which are known as vapor pressure and intermolecular interaction. Intermolecular interaction ये तो आप लोग को पता ही है क्या होता है कि it is the interaction attraction between the molecules between, okay, and vapor pressure वो हम लोग डिस्कस करेंगे. And here in this topic we are covering the three important topic which are Raoult's law, ideal and non-ideal solution, and the positive deviation. So what is vapor pressure? So when I say vapor, vapors means when this liquid is changing into its gaseous state, correct? So when I take a closed system, in this closed system like any particular component is present and I am applying temperature into it. So what is the tendency of these molecules? The liquid molecules will try to escape from its liquid state to its gaseous state, okay. It will try to transform, it will get transformed, and what will happen? It will just heat the container because the system is closed. So since it is heating the container, they will lose their kinetic energy, and for which they will again come back to its original state, okay. Condensation will occur, and this coming back will also exert some pressure into the surface of the liquid. That particular pressure exerted by these vapors are known as vapor pressure, okay. So what is the role of vapor pressure in Raoult's law? So when I say Raoult's law was a scientist who gave the statement between those solutions where the solute and solvent are in liquid state. So when I mix two particular solvent, okay, solute A and solute B, so they will have an amount of interaction between them. It can be strong, it can be weak, right? So based on the interaction, when I apply heat, if it is weak, then within a small amount of heat they will break the intermolecular attraction between them and they will come back to its original state, right? Component A and component B in the solution, and after that they will reach their boiling point, and that after reaching the boiling point, what will happen? They will try to escape from this particular container, but since it is closed, so what will happen? Vapor pressure will exert in this particular system. So how vapor pressure is playing the role? It is playing the role in this way that the partial vapor pressure exerted by any one component in this particular solution is directly proportional to the solubility of A and B, okay, and the concentration of A and B present in the solution, which can be also written as PA is directly proportional to the mole fraction of A, right? And after that, when I remove this proportionality, then what will happen? A constant term PA naught will come and this side XA. This PA naught is actually the vapor pressure, the partial vapor pressure when this component was alone, was in its pure state. तो प्योर स्टेट के लिए जितना वेपर प्रेशर आएगा उसे हम लोग PA नॉट मानते हैं. PA कब मानेंगे? जब ये पर्टिकुलर वेपर प्रेशर फॉर्म होगा इन द सॉल्यूशन. अगर मेरा सॉल्यूशन A का वेपर प्रेशर एक्सर्ट हुआ है तो उसको हम लोग PA मानेंगे, और XA इज द मोल फ्रैक्शन ऑफ A प्रेजेंट इन द गिवन अमाउंट, ओके. सिमिलरली PB, ओके, एंड अकॉर्डिंग टू Dalton's law we know that total vapor pressure is equal to sum of the partial vapor pressure, that is PA plus PB. And when I put the equation, when I put the value of equation A and B, like if I consider it A and this side B, and I put in this particular equation, then it will come to be XA PA naught plus XB PB naught, okay. And I know that in a binary solution XA plus XB is always equals to unity. So I can write in place of XB, I can directly write 1 minus XA and just put the value of XB in this equation, and it will be XA PA naught plus 1 minus XA PB naught. Okay. So this was the equation given by Raoult's law, and in this particular statement, in this particular law, we are going to see some key points is that ideal solution, okay, if this particular law is followed, then those particular solution will always be your ideal solution. Okay. Ideal solution means what? Like when a particular solution is formed between similar type of molecule. For example, if I take bromoethane or chloroethane, the structure is almost the same, right? So what will happen? They will just occupy the space between the liquid and it will be just a homogeneous mixture. Okay. So those type of solution will follow the Raoult's law, and the vapor pressure is directly proportional to the mole fraction. After that, if I want to see the graphical representation of Raoult's law, then it is in this way. Okay. Here vapor pressure is taken in the x-axis and mole fraction is taken in the y-axis. Y-axis is our vapor pressure and x-axis is the mole fraction. So consider this two, actually why it is written like this, actually this is a two graph. These two graphs are combinedly presented to us. So if I take XA equals to 1, so after some time what will happen, the concentration will decrease since XB means the component B is getting added into it. So for which your A component concentration will decrease and it will be 0, and this side B will come to be increased and equals to B, it will be equals to 1. Similarly in this side also we can see the similar thing. First I have taken B component and I have added A into the solution. So these are two graphs which are combinedly presented to us. So when I see the graph, any one of the line, okay, any one of the line will be a little bit higher than the other one, which states that if it is upside, that means my PB naught, for it is coming for PB naught, right? That means my XB is more volatile than XA, for which it will reach its boiling point fast and it will exert maximum vapor pressure than the A component. Okay. So this is the graphical representation of Raoult's law. Now we will move to the another topic known as ideal solution. Ideal solution and non-ideal solution means ideal solution will obey the Raoult's law, and if it obeys the Raoult's law, the graphical representation will always be the same. In this particular ideal solution, the change in enthalpy means the amount of heat released or absorbed, okay, it will be always equals to 0. मतलब जितना absorb किया है energy bond breaking के लिए, उतना ही amount of energy वो release करेगा, ठीक है. After getting the component broken, it will again come back to its original component, right? So उसका जो delta H का value है वो already 0 ही होता है. And change in volume, there is no change in volume since the intermolecular attractions are almost the same, the structure is almost the same. That is why the volume will not be varied, okay, it will be always equal. So that is why delta V value comes to be 0. Here we will see examples of bromoethane and chloroethane. So both the components are of similar structure, और अगर similar structure है तो उनके बीच में जो attraction है वो बस वो space ही occupy करता है, कोई वहाँ पे like कुछ अलग टाइप का रिएक्शन नहीं होता, ठीक है. इट विल जस्ट ऑक्यूपाई द स्पेस, जैसे ब्रोमोइथेन बैठा है वैसे उसके बीच में क्लोरोइथेन देन ब्रोमोइथेन, लाइक दिस दे विल जस्ट ऑक्यूपाई द स्पेस एंड इट विल बी यूनिफॉर्मली डिस्ट्रीब्यूटेड, ओके. एंड द सेम द अमाउंट ऑफ हीट absorbed to break the bone and release, it will be same. So that is why it will behave like an ideal. Also you can see benzene and toluene. Benzene structure is like this, this is our benzene, and similarly my toluene is this. So इस इन दोनों के बीच में जो attraction होगा it will be the same. Again here I will place the benzene, so almost the similar distribution, similar arrangement. That is why these are example of ideal solution. Now coming to non-ideal solution. Non-ideal solution doesn't behave the Raoult's law. So if doesn't behave the Raoult's law, the graphical representation will be a slightly different one. Here we see that the change in enthalpy will not be equals to 0 here. Okay. Here the delta H value will not be equals to 0, and also the volume, change in volume will not be equals to 0. Okay. And there are two types of non-ideal solution, one is positive and the other one is negative. Positive deviation occurs when the interaction, if the interaction between AA component or BB component, if the interaction between AA or BB interaction are more stronger than A and B, then what will happen? My solution will form AB in the particular mixture. My AB bond will get formed, but within a small amount of temperature, they will again break their bond and they will come back to its original state. So for which there will be a deviation in the graph, and it will show you the positive deviation. Okay. And नेगेटिव डेविएशन क्या होता है? नेगेटिव डेविएशन में ये जो ए के बीच में इंटरेक्शन है या फिर बी के बीच में इंटरेक्शन है वो वीक होता है कंपेयर टू ए एंड बी. फॉर एग्जांपल मोस्टली पॉजिटिव डेविएशन इज फाउंड बिटवीन अ नॉन पोलर एंड अ पोलर सब्सटेंस. ओके, like you can see clearly here. So this type of molecule will do what? They will form the weak intermolecular attraction, but within a small temperature again they will come back to their original state, and so they will reach their vapor pressure, the vapor state. After reaching the boiling point they will get transformed into vapor state, and then it will exert the vapor pressure more positively. But in negative deviation there is a strong attraction between the two molecules, and due to that strong attraction between the molecules you have to apply more temperature to break the bond. So that is why they will be showing you a negative deviation, and these are some example: acetone, chloroform and hydrochloric acid and water. We know this type of bonds are more stronger, right? Our HCl and water will react together and it will form hydronium ion plus Cl negative in the solution. So we can clearly see that here the interactions are more more feasible than the previous one. So that is why they are showing you the negative deviation. How it occurs, like if I take both the spaces, like spaces A and B, for an ideal solution the mixture is very uniformly distributed. They just occupy the place and it is uniformly distributed throughout the solution. But when I see the non-ideal solution, the distribution will be, they will have an attraction, they will have a weak or strong attraction, but the molecules will form in this way. Like there कोई क्या होता है कि उनके बीच में एक हाइड्रोजन बॉन्डिंग होगा, दूसरे के लिए भी होगा, किसी में नहीं होगा, रिपेल होगा, फिर किसी में नहीं होगा. तो इस तरह से मतलब वो लोग डिस्ट्रीब्यूट होकर रखते हैं. ठीक है, they will have a weak interaction or they will have a strong interaction. For example, here you can see that both the components are of same type, but they are having a good attraction between them, this side also and here also. Okay, so these are some like just an molecular representation how AB is showing you the repulsive interaction for a non-ideal solution, and this side how ideal mixture is formed. Okay, they are having an attraction between them like this. Now if I take this is my ideal mixing, right? This is my ideal solution, completely uniformly distributed. But if I take a non-ideal behavior showing positive and negative deviation, for positive deviation the AB interaction is weak, and since it is weak, within a small amount of temperature they will just break the bond and see how the components are coming to its original state. And similarly, when I see a negative deviation, they are having a strong attraction between them. Due to this strong attraction, only few components, only few molecules of A and B are coming to its pure state, okay, in the solution. So it will absorb more temperature to break the bond between the molecules, between the intermolecule, and then come back to its vapor state. So that is why it will show you a negative deviation. Now this is a graphical representation. The dash line is for the Raoult's law. Okay. So if the positive deviation is seen, positive deviation के लिए क्या होता है कि minimum boiling temperature में ही ये अपना bone break down करके अपने कंपोनेंट स्टेट में आ जाता है, ए या फिर बी, ठीक है. तो उस फॉर्म में होने से क्या होता है, हमारा ग्राफ आना तो चाहिए था इस तरह, बट इट विल कम स्लाइटली टिल्टेड लाइक दिस. ओके, दिस इज शोइंग द टोटल वेपर प्रेशर. पी ए और पी बी को जब हम लोग प्लस करेंगे तो उसके ऊपर ऐसा आएगा, ठीक है. दिस इज फॉर द रावल्स लॉ, और यू कैन से दिस इज द आइडियल सॉल्यूशन फॉर द डैश वन, एंड दिस आर फॉर द पॉजिटिव डेविएशन. And when I see the negative deviation, for negative deviation what happens? Okay, ये ग्राफ थोड़ा सा गड़बड़ हो गया. यहाँ पे क्या करना है कि for negative deviation it will come in the downside. Here I have shown you for PB, this is, and for PA it will come a little bit this side. Okay, if I want to show you properly, then it will be in this way. Like this is my graph. Here I have taken vapor pressure and this side mole fraction. Okay, sorry, mole fraction. So I will join these two graphs. For Raoult's law it will be like this. This is my Raoult's law graph. Here it will be for PB, this side PA, and here XA equals to 1, here XB equals to 0, this side XA equals to 0 and XB will be equals to 1. So अगर रावल्स लॉ फॉलो नहीं करता है तो वो अगर नेगेटिव डेविएशन दिखाएगा, मीन्स ए बी के बीच में स्ट्रॉन्ग इंटरेक्शन है, सो ऑब्वियसली इट विल एब्जॉर्ब मोर टेम्परेचर टू ब्रेक द बोन. सो मैक्सिमम विल बी द बॉइलिंग टेम्परेचर, एंड फॉर विच योर ग्राफ will be a little bit downside. Okay, and this side it will be for here, and this is for the P total. ये P total होता है जब रावल्स लॉ फॉलो करेगा, तो अगर नेगेटिव डेविएशन है तो उसका भी थोड़ा सा डाउनवर्ड आएगा. ओके, सो दिस इज ऑल अबाउट आवर today's discussion. That is, we have already covered the Raoult's law, ideal and non-ideal behavior in that particular solution, and how this non-ideal solution will show us positive and negative deviation depending upon the intermolecular interaction between the two particular components present in a solution. So that's all for today. Thank you.